week, we have with us, first of all, Vincent Van Hemelryck from Uppsala University, and he's going to talk us about scale-separated AdS vacua with G2-structure manifold. Vincent?
Yes, thank you, Nacho and George, for inviting me to speak here and giving me the opportunity. So indeed, I will talk about two works, one that appeared last summer and one that actually appeared yesterday on arXiv. And it's indeed about this scale-separated AdS vacua on manifolds with G2 structure. And this talk will consist of two parts. So in the first part, I will talk about the first paper, which is about a proposal for scale-separated AdS4 solutions in M-theory. And then in the second part, I will talk about the results that appeared yesterday, which are such solutions, but in type 2b. So before I start, I want to remind you what this scale separation is all about. So I think that all of you are familiar with the notion of string compactifications. So string theory is the best theory of quantum gravity that we have to this day. And it appears so that the best version of it is 10-dimensional in nature. And in order to obtain lower dimensional theories from it, well, we use compactifications. And what we usually do is we take a maximally symmetric space-time that is non-compact, and we consider an additional compact space, which I denoted here by Mn. And this compact space has intrinsic scale to it, which we call it the Kaluza-Klein scale, which parameterizes how big this manifold is. And additionally, the external space-time has a cosmological radius. You can think of this as the AdS radius or the de Sitter radius. And requiring that you have a really truly lower dimensional effective field theory amounts to this compact manifold to be small compared to this AdS radius. So, and that is what we call scale separation. So you require that the KK scale is much, much smaller than the AdS radius or the Sitter radius. And in terms of mass, in terms of energy scales, it means that you want the cosmological constant to be much, much smaller than the KK mass squared, which here you can think of also as providing you for you the cutoff of your effective field theory. And this KK mass squared is also related, of course, to the lowest eigenvalue of some generalized Laplacian operator. So if you are interested in obtaining genuinely lower dimensional effective field theories in this way, you typically want that also with full moduli stabilization, meaning that all the scalars that parameterize the sizes and the shapes of submanifolds in this manifold, that they are fixed, that there are no fluctuations that would bring it to arbitrarily large or small values. So you really want that to be fixed. And in the first part, in the first paper that I want to talk about today, I claim to have found evidence, at least, for the existence for supersymmetric, scale-separated 4D Freund-Rubin solutions of M-theory on weak G2 manifold. I know these are lots of words, but these will all be explained. And I want to start by reminding you of what Freund-Rubin solutions are in string and M-theory. So these are actually the most simple compactifications you can imagine. So again, you write your spacetime as a product spacetime, and your internal manifold is positively curved and will turn out to be important. And due to the positive curvature, what this manifold usually wants is it wants to contract it wants to collapse under its own weight. And that's why we introduce a flux that fills the whole dimension, so it threads the whole internal manifold to kind of counteract that collapse. And you can do dimensional reduction of this theory down to d dimensions to study where the stable radius of the sphere is. But it turns out that it's also relatively easy to solve the higher dimensional Einstein equations. And when you do so, and you look at the components in the external spacetime, you will find that it's negatively curved, and also that the metric has to be of Einstein, since the curvature is proportional to the metric. And so since it's negative, it means that this has to be an AdS spacetime. But also the internal spacetime has an Einstein metric, and the proportionality constant is positive, meaning that this internal space must have a positive Einstein metric. And it turns out that these proportionality constants are, well, they depend on dimensionality factors. And so this means that both the internal and external curvature are related up to an order 1 dimensional factor. And as you all know as well, the external curvature is also related to the cosmological constant, meaning that all of these curvature scales, they are parametrically the same. So when this positively curved Einstein manifold is, for example, a sphere, because spheres are such manifolds, and when that sphere has a radius L, then it turns out very trivially that the curvature radius is exactly the same as the radius of the sphere, right? And since the radius of the sphere is a good measure for the KK radius, and hence the inverse KK mass, it turns out that since all of these curvature scales are related, that the cosmological constant must be of the same order of the KK mass squared. And so you do not have scale separation. You can only obtain scale separation in such a way if this curvature would decouple from this Kaluza-Klein length scale. Okay, so there are many examples in string theory and M theory where this scale separation feature in Freund-Rubin vacua does not occur. Think of AdS 5 plus S5 in type 2b, or AdS 4 plus S7, or AdS 7 plus S4 in M theory. But this turns out to be more generally true in string compactifications. Even when you have more complicated manifolds, many more fluxes that thread some cycles and so on. Nevertheless, there are a handful of examples with scale separation, which have been discussed in many talks, in conferences and so on. The examples that most people know about are the so-called DGKT, vacua, KKLT, LVS. There are 3D variants of these as well, considered by these people. But nevertheless, they are under criticism, although I think many of these criticisms are actually being refuted. But nevertheless, I will not talk about these things here today that much. Additionally, there are also recent arguments against scale separations for supersymmetric theories that typically preserve more than 4 supercharges, considered by these people here and others. And it must be said that these examples here, they typically preserve less supersymmetry and evade these arguments. So that is why they are special. And moreover, there are many theorems and swampland conjectures that say something about scale separation that's restricted in certain scenarios, which is, for example, considered in these papers here. But I will not discuss this too much. I just want to illustrate that this is a well-debated issue in the context of string phenol. But I advertised that I want to consider scale separation for Freund-Rubin vacua. And so what this actually means, as I told you before, is that this curvature, well, I will consider M theory down to 4D. So it means that since all of these curvature scales are related, that the 7-dimensional curvature must be much, much smaller than the KK mass squared. And since the KK mass squared is just related to the lowest eigenvalue of the scalar Laplacian, it means that this curvature needs to be positive and much, much smaller than the lowest eigenvalue of the Laplacian, of course, which is a purely geometric condition. So the scale separation condition is just a purely geometric one, and there is no debate in this sense about whether there is a back reaction from orientifold planes or whatsoever. It's purely about the geometry. Now, it was conjectured that something like this for positively curved manifolds is not possible. That was considered, that was actually formulated as a conjecture in this paper. And what I want to argue for today is that this manifold that I've studied might be a counterexample to this conjecture. But also note that this decoupling of scales here is something that is known to happen for negatively curved manifolds. For example, for nil manifolds, for solved manifolds, the lowest eigenvalue of the Laplacian is always, can be tuned to be much, much larger than the curvature. And it is also true for a 6D nil manifold that is called the Iwasawa manifold that will play a special role later in this talk. And so the strategy to realize this decoupling is by actually considering a scale-separated solution of massless type 2a on such an Iwasawa nil manifold that has this decoupling of scales, and lift that solution to M theory, which turns out to be a Freund-Rubin solution of M theory, where that decoupling of scales still persists. In type 2a, this compactification that you would consider is one on a manifold that has SU3 structure, and in M theory, it's on a manifold with G2 structure. And you can do, of course, this lift, because as you know, strongly coupled massless type 2a is the same as M theory with a large circle, and where the size of the circle is indeed given by the dilaton or the string coupling. So let me maybe also say what I mean with these SU3 and G2 structures. It's a whole topic, of course. But what is the most important for this talk is that what it means is that that there are transition functions, of course, that bring you from one patch to another on a manifold, and that these transition functions are an element of a group. And for SU3 structures, that group is SU3, and for G2 structures, that group is G2. And the most important part for the story here is that the metric on such spaces can be completely encoded into differential forms. For an SU3 structure in 6D, that is a scalar 2 form J and a holomorphic 3 form omega, as many of you might know. And for a G2 structure, that is a 3 form phi and its Hodge dual 4 form star phi. And the curvature can also be encoded into something nice, which are the torsion classes. And the torsion classes, they inform you on how J and omega for an SU3 structure are not closed. And the same for G2 structures, how phi and star phi are not closed, right? So as I said, the idea is to take specific massless type 2a solutions, more precisely ones on SU3 structures, and they preserve n equals 1 supersymmetry. And such solutions have been studied in the past by many, many people. And for massless type 2a, they can be summarized as follows. So all of the fluxes can be written in terms of the geometric forms J and omega, and also some warping, which is, the warping is called A. And as you see, there is also this parameter M tilde, which is the inverse AdS radius. And particularly here, there are only two fluxes that are non-zero. That's F2 here and F6. F4, F0, and H are 0. And maybe you're not familiar with this J to the -1. It's not that important, really, but it's just nicer to work with this operator that contracts this form with the inverse elements of J instead of working with a Hodge dual operator. Moreover, the warping and the dilaton are related in such systems, and the manifold cannot be just flat. It needs to belong to this half-flat class of SU3 structure manifolds, which means that some of the torsion classes are turned on. And here you have one in the trivial representation of SU3. So, and that one is actually related to this inverse AdS radius. And there is also a primitive 2 form W2. And of course, like a 1 form that is related to the warping. So if you have a background of this type, well, it solves the supersymmetry equations, but you also need to impose the Bianchi identities. And in this case, there is only one that is non-trivial, and that is the one for F2. And so you might need these 6 branes or orientifold 6 planes, which are negative tension objects, codimension 3, to make sure that this Bianchi identity is satisfied. And so this means that also F2 needs to be closed everywhere except up to the loci of some of these sources, right? So the nice thing about these SU3 structures is that if you want to lift such solutions into M theory, that you can actually do that into G2 structures. And this is already understood. There are these formulas are written all over in the books, and it's simply given by these expressions. And the takeaway message here is that both phi and star phi can be written in terms of the SU3 structure forms J and omega, and also the warping and the dilaton. And there is also a one form, which I call V, which encodes the M theory circle. So what you do is you fiber basically the six-dimensional manifold non-trivially of a circle, and the connection that you use there is basically the gauge potential for F2. So that means that this one form V is not closed, and that its exterior derivative is equal to, in this case, minus F2. Okay. And then if you compute the exterior derivatives on these forms and use this massless type 2a solution in its generality that I've highlighted in the two previous slides before, then you end up with these two very simple equations. So d star phi is 0, but phi itself is not closed, but is proportional to star phi. And that means that this 7-dimensional manifold that arises from this SU3 structure has weak G2 structure. And you have weak G2 structure from any massless type 2a background with n equals 1 supersymmetry in 4D. And this argument does not depend on the types of sources that you have. So you can have local sources if there are any. Okay. So weak G2 manifolds, they are actually very special because they are positive Einstein. So it's only one torsion clause that is turned on. And indeed, the curvature is proportional to the metric, and the proportionality constant is given by this torsion clause. And again, such positive Einstein manifolds are very useful for Freund-Rubin solutions. And moreover, these weak G2 manifolds, they preserve n equals 1 supersymmetry in 4D. So you can find supersymmetric solutions of this type. So the idea then, of course, is to specify now to a very particular SU3 structure solution in massless type 2a, and that is the scale-separated solution that we have discussed and studied in this paper from some years ago, which is a compactification on a specific nil manifold, which people call the Iwasawa nil manifold. And there are F2 fluxes and F6 flux and orientifold 6 planes. And then through the machinery, it leads to a scale-separated Freund-Rubin solution of M theory, because you can check that the cycles or you can estimate that the cycles in this manifold are indeed smaller than the AdS scale. And this F6 flux, it leads to a G7 flux in M theory. But what is very important here is that this argument applies as long as F2 is closed locally, because I argued that the exterior derivative on V is proportional to F2, meaning that if I compute the second derivative on it, I get basically the Bianchi identity of F2, which needs to be 0 everywhere up to some singularities which might get resolved into M theory. So you cannot do this lift when you consider a completely, a solution wherein these O6 planes are completely smeared. And that is what usually people do. Now, it is actually possible to treat these O6 planes as the local objects that they are using perturbation theory. And that is actually something that we did a couple of years ago by solving the 10-dimensional Einstein equations and looking at corrections for the metric, but also all the other quantities in the equations. But in order for this argument to apply, you need to know how the SU3 structure forms are corrected due to this O6 plane back reaction. And that is actually the hard calculation in this paper that I did. But due to time constraints and not to bother you with too many complicated equations, I will not show you, and you have to believe that you just have to believe me that it worked out. So with that, I want to switch to the next part about what appeared yesterday on the archive. How much time do I?
Yeah, you have 5 minutes.
10 minutes.
Let's try to make them shorter.
Okay. So yesterday I had a paper on the archive about new supersymmetric scale separated solutions in type 2b. And so the idea there is exactly the same, but just slightly different, of course. And so what you do is you consider AdS3 solutions of type 2b on G2-structure backgrounds instead of SU3 structure backgrounds. And these are things that people have studied in the past before. And so for such backgrounds, it turns out that the G2 structure needs to be closed. So supersymmetry imposes that, meaning that now there is an additional torsion class that is turned on. So that's this W27. And again, the fluxes are completely determined in terms of the geometry, this time not by J and omega, but by phi and star phi. And so only F3 and F7 are non-vanishing, and all the others, well, they are zero. And again, there is a non-trivial Bianchi identity which needs to be solved. And note here that there are no war factors or dilatons appearing because I've set them to 1, so I'm working in a smeared limit for these sources. So this has been considered before, but not really on very specific manifolds that generate this scale separation feature. And that is actually the new thing that has appeared yesterday. So what I considered is a very specific manifold. It's a so-called 7-dimensional manifold, which can be regarded as 3 copies of the same 3D solved manifold where one direction is common. And this 3D solved manifold arises from a solvable algebra, which is encoded by this here. And I forgot to say that the 7th one form is closed. And well, you can integrate them and so on. But I think there is a cool picture to it. You can regard it as a circle times a 2 torus. And when you go around the 2 torus, actually the wheel binds, they rotate at every point in this manifold on these 2 torus. And so you have 3 copies of those with 1 common direction. And when you consider such a solved manifold, you can impose an orbifold action on it. And I consider 2 of them, very similar to what Joyce considered when he wanted to construct G2 holonomy spaces from T7 orbifolds. And it turns out that if you do so for this 7-dimensional manifold, you get a co-closed G2 structure. And when you supplement that with an O5 involution, you get 2 different situations for these 2 different orbifolds, where you generate 1 set of 5 planes, and in another case, 4 sets of intersecting O5 planes, or 4 intersecting sets of O5 planes. And this one here is very similar to what people in Oviedo have considered last summer as well. And so again, what you can do is take that manifold, look at its look at the torsion classes and so on. Look at how the supersymmetry equations that I've shown before, how they relate everything. And it turns out that for such a manifold, well, this is a horrible formula, I know, but you can write phi as a sum of 7 treeforms, and the same for the treeform flux. And all these moduli, these S's here, they are fixed by all of the fluxes, all the treeform fluxes and the 7-form flux, and the dilaton as well. And it turns out also that if you compute DFF3, then you get either 1 or 4 components. That depends on the orbifold. And moreover, it's only sensitive to these components over here. So these components are closed, meaning that the fluxes in blue here, they're not constrained by tadpoles, and they can be tuned towards infinity. And since everything depends, all the moduli depend on these fluxes, well, you have some freedom to play with. And if you compare the 3-cycle volumes with the AdS scale, you see that, for example, for this one, it indeed scales like 1 over some flux parameters that you can tune to infinity, and hence, when you do so, you obtain scale separation. And that can also be obtained while having weak coupling and large volume for all cycles. So in that sense, it's in the controlled regime. Moreover, lately there has been a lot of interest in scale-separated solutions of type 2 theories, and people have noticed that this leads usually to integer conformal dimensions for the putative dual operators, and here it turns out to be the same. So for the example with 4 sets of 5 planes, they are integer up to a specific choice of these omegas, but it's not very hard to achieve so. So for example, when all of these faces, so all these geometric fluxes are the same, and then this conformal dimension is integer. And for the one set of 5 planes, it's the same. They're also all integer. And I also want to highlight that especially this solution that I have here, it picks already as precise values of these omegas, or at least a relation between them. And it turns out that this is a supersymmetric vacuum, a supersymmetric version of vacuum that was already found by these people in Oviedo. So it's basically a skew-waved version of the one they found. Good. So now I come to the conclusions. So I've told you for M-theory and Freund-Rubin solutions that they can only be scale separated when the curvature decouples from the lowest eigenvalue of the Laplacian. And there is evidence for this in M-theory with a weak G2 structure from lifting a scale separated solution of massless type 2A. But it's very crucial to treat the O6 plane sources as local objects, so doing computing the back reaction, which I've not shown to you, but I want to emphasize that it's crucial. And for future directions, it would be interesting to understand this manifold a bit better from geometrical picture, and also contemplate what this might mean for the holographic dual theory. And for the type 2b part, I have formulated new supersymmetric scale-separated solutions, which to my knowledge are the first supersymmetric solutions with scale separation in type 2b that are well controlled in the large flux limit. And I have situations with 4 sets of O planes or with 1 set of O planes, and they have integer conformal dimensions. And for future directions, it's interesting to look at the usual things like plane back reaction, blow up of orbifold and of orbifold singularities, and maybe look for more realizations of scale separation with different kind of manifolds. And with that, I would like to thank you for your attention.
Thanks a lot, Vincent. Is there any question from the people in the audience? Yeah, so George.
Can you hear me?
Yes.
Yes.
Okay, congrats, Vincent. I do have a question. You mentioned that actually in your last slide. So we have performed this expansion method, this perturbational defined corrections in type 2A constructions, like in DGKT, to calculate the back reaction. But since in your setup, in type 2B, you have like a free parameter, I guess that you can perform this expansion method. But at leading order, your geometry is more complicated, I guess. So you think it's going to be harder to find the back reaction and solve the equations?
It is definitely going to be harder than when the manifold, is flat. So for DGKT, this has been done both by Daniel Junghans and then by also Macesano, Balti, Kirand, and Tomasiello. And so there we know how it works. For manifolds that are curved, for example, in this massless type 2A setting, the manifold is curved. Your O-planes also wrap generalized cycles. They're not cycles in the proper sense, but the associated volume forms are also not closed. And there it was indeed not trivial to do the localization, at least from the perspective of the SU3 structure. But at the level of the Einstein equations and the equations of motion, just like Daniel Junghans did for DGKT, well, that's what we did in the past. And I think here is going to be the same. It's a technical issue, I think. You can probably just do it at the level of the equations of motion, 10D Einstein equations, but that, of course, does not inform you too much about supersymmetry. You do not impose supersymmetry there. So if you want to do it within supersymmetry, in a supersymmetric ansatz, you need to still do it in terms of a G2 structure or a generalized G2 structure. And this is actually much more complicated to do. So I think it's just a technical issue.
Okay, thank you. Thanks, Vincent.
Thanks. Sap?
Vincent, thank you for the nice talk. I just want to go back to the type 2A solution for 1 second, just to make sure I understand the net statement. So when you lift your type 2A to M theory, the O6 planes go away. You should be left with something that's pure geometry. So the claim is that there's a pure geometric solution that has scale separation at the end.
Yes. Yes.
Okay.
Of course, we have to be fair here, and it's not that we have the full metric or so of this space, but we at least have one that, well, we have a metric and we have a geometric description in a perturbative scheme. So we have it at leading order, but it's not that we at the moment fully understand how the O6 plane singularities get resolved. Of course, I can say the words Atiyah Hitchin and so on, which might resolve these singularities, but to see that concrete calculation is something that we do not have. But that is at least a hope. And that is where I hope and think that this construction does better. And indeed, if you are able to just find a positively curved manifold or positive Einstein manifold where this decoupling of scales works, whether it's related to our construction or not, then the scale separation debate, in my opinion, is over, because then the geometry just does it for you.
Very good. Very good. Great. Thank you.
Okay, thanks, Vincent. So can you please stop sharing the screen?